Okay, let's start. Any questions? So we were discussing about nonlinearity, right? And how to, we discussed about what are the measures of nonlinearity in most RF systems. And by the way, even though I introduced these measures like P1, DB, P3 for narrowband IF systems, narrowband RF systems, I mean, you can obviously extend them to any type of system. So as it turns out, even in wideband systems, people use those matrices to characterize their circuits. I mean, it can be receiver, it can be any amplifier, it can be filter, but still these IIP3, P1 dB numbers are often quoted. Right? So even though strictly speaking, they were introduced for RF, but they have generic use. So having said that, so let's start off with let's continue the discussion we were having. So we were discussing about how to bias this transistor and what are the effects if we bias it with different types of overdrive voltage, right? So if I bias it with some VGSQ, and I am interested in finding out IDS, what did we see? We see that higher V overdrive correlates to better linearity. And we did this with only second order distortion, second order nonlinearity, but it did not necessarily be the case, right? So it can be for any order nonlinearity. The reason it is difficult to show any order nonlinearity in this particular context is because the square law, the very simplistic square law model that we take for the MOSFET does not, by definition, allow you to go to higher harmonics, right? So if you want to see the effect of higher harmonics here, and then you obviously have to use some other model of the transistor. And for those of you who have taken device courses, you will see that obviously the more complicated or more involved model of the transistor has some multiple variables, right? And we do not want to go into those complicated equations, but in order to get an idea, you can appreciate the fact that for short channel devices, I assume you know this, for short channel devices, the current voltage relationship is not square law, right? It's not VGS minus VT whole square. That's because it's something times VD sat, right? So it's because there is a velocity saturation that comes into picture, and when you typically derive the square law model, there is one condition for pinch off and one condition for yeah, when you integrate, you get another condition, and both those get multiplied and you get squared. If you have velocity saturation, then those two conditions are not the same, so you don't get the squared, you get the linear term. Now, if you just simply go by the linear term, you might be thinking that a transistor is perfectly linear device, right? That also is not true. So truth is always between these extremes. It's neither like fully linear nor square. A very crude hand wavy model is, if you want to get a rough idea, you can assume it to be some constant. I'll call this some C times VGS minus VTH whole to the power m, right? Where m is probably somewhere between 1 and 2, right? So again, this is also not a physical model. I mean, if you curve fit in saturation, you are going to get something like this, but there will be a whole bunch of other terms also. The reason this is intuitive is because I mean, I shouldn't say intuitive. The reason this is more helpful is because So when you have something to the power m, where m is a fraction, then obviously you can have a Taylor series expansion of this, which has all orders of power, right? And note that this is overdrive to the power m. So if you expand this around some quiescent overdrive, you are going to get all sorts of Taylor series expansion around VOV to the power m. VOV to the power 1, VOV to the power 2, 3, and so on, which naturally means that you should be able to extract the information of third order distortion or fourth order or fifth order or whatever from this simplistic equation, right? So that is one of the reasons this is also useful. But having said that, this doesn't have any physical meaning, right? So this is one of those things which you can get from curve fitting. Again, strictly in saturation, this will fit. Obviously, this will not fit when you are going close to the linear region. Fine. So that is to give you an idea of how square law models are inadequate. But the key thing to note here is that even if you do the analysis using this, I'll not show you here. You can do this on your own. Extract the expression of G3, extract the expression of G4, G5, whatever, and then see what needs to be done to minimize those contributions. So clearly you will see that, I mean, if you have to do G3, you have to differentiate it thrice. If you differentiate it thrice, you are going to get VGS minus VTH whole to the power m by 3, m minus 3, right? So you will see that even when we want to reduce that, you would like to have maximize the overdrive voltage, right? So that's as far as this explanation. This can be. We did this in the last class where m is equal to 2. The point that I am trying to drive home here is that even if m is not equal to 2 is some fraction also, if you do the math, it will come out as your linearity increases if your quiescent overdrive increases. Okay. So what are the ways? So basically, one way to improve linearity that we understood, handles, what are knobs to improve linearity. Since we are talking about distortion, I'll just say distortion performance. Increase V overdrive. That definitely is one knob. Now, the issue with increasing V overdrive is naturally you should appreciate that you cannot have overdrive voltage to be equal to VDD, right? Because you need some swing at the drain voltage also that you will not get. So you are essentially limited. So given that you are limited by some overdrive voltage, what other knobs can we explore? So from your understanding of, or from your experience in doing analog circuit courses, you should readily appreciate the fact that if we can use feedback, then feedback reduces distortion, improves performance. But the issue with using feedback in RF circuits right away is the fact that these operate at fairly high frequencies, like gigahertz, 2 gigahertz, something like that. So if you use negative feedback, then which means that the loop gain should have decent, high enough loop gain. You should have high enough loop gain at those frequencies. It is, yeah, right. So let's say you want like 20 dB gain, loop gain. I'm just throwing out a number. Let's say you want 20 dB loop gain at 2 gigahertz. And if you want this 20 dB per decade roll off, which means the UGB should be like 10 times that of 2. That's not very trivial to design, right? Another problem with that is that, you might be able to design something which has decent enough unity gain bandwidth, but you should also appreciate the fact that this negative feedback reduces this distortion or improves linearity. It works under the assumption is that the loop gain also has, at the frequency of interest, the loop gain also has 0 phase, right? If it also has a phase lag, then the two input, negative feedback works under this Negative feedback works under this assumption, right? If you have VI, this is V feedback, this is V error. So everything is good as long as V error is 0, right? Or close to 0. And that can only happen if VF is exactly equal to VI, both in magnitude and phase, right? So if VF is not exactly, also not in phase with VI, then VE will not be equal to 0, right? So it's not only sufficient to have high loop gain, you also have to ensure that the phase with which it comes, the phase lag essentially between VE to VF is not significant, right? And that is a far more difficult thing to achieve at higher frequencies because phase starts to roll off pretty quickly, right? So that is why if you are doing multi-gigahertz design, right, so it's difficult to use feedback, right? So introduce negative feedback obviously is a generic hack that one might want to explore, but at high frequency it's a problem, right? So negative feedback can help. I'm not ruling it out, depending upon your ability to design high frequency feedback loops, but it's difficult at high frequencies. Okay, so what else? So now, if negative feedback cannot help, then we have to obviously look into other ways of improving. Now, I'll show you a couple, but they are obviously not ubiquitous. There are other ways of improving also, but the couple that I'm going to show you will probably help in your design going forward. Yes. Yeah. Yeah. Oh, that depends on the small signal. I mean, that you have to find out the phase margin of the loop, right? So that's what essentially phase margin is telling us, right? Phase or gain margin, assuming this is like monotonically decreasing transfer function. So then you'll have to evaluate whether, I mean, for example, if VF is exactly 180 out of phase with VI, then it's an oscillator, right? So between getting to oscillator and being perfectly stable, there is a whole bunch of phase lag possible between 0 to 180. Right? So it is going towards instability if the negative if the phase lag at around UGB is getting closer to 180 degree, but need not necessarily be. But what I meant by this is that let's say you have designed a loop which is stable, right? 60-degree phase margin, 70-degree phase margin, no issues. No issues with instability. But you are and let's say you have decent enough gain at 2 gigahertz. The loop gain, let's say, is 20 dB. But let's say loop gain is 20 dB, but let's say the phase lag is also, I mean, some 90-degree phase lag. 90 degree is not correct. So let's say 60-degree phase lag from wherever you started, right? Which essentially means that if VI is something like this, your VF, instead of being exactly in phase, will be probably something like this, which means that you are subtracting to sinusoids which are out of phase, which means VE will also have a swing. Right? Now, VE directly goes to the input of a nonlinear block. LS is nonlinear, which means its output will become nonlinear. The whole reason this negative feedback, VF is 60-degree out of phase with respect to VI. Sure. Sure. Yes. Effectively that.
Might happen that VF and VI will become very close to each other.
Whether it will happen or not, that's the whole function of the loop, right? So in the sense that ultimately, how do you know what is VE? So if your VE is essentially, this is the error, right? So this is inversely proportional to loop gain, 1 plus L of j omega, right? So now, I mean, at your frequency of interest, so this is approximately equal to 1 by L of j omega, right? If L is sufficiently higher than, if your L is sufficiently higher than D, I mean 1, correct? So now the point that I was trying to make is that if L is like 60 dB or something, then there is no issue, right? But if L is 20 dB, which means gain of 10, right? So then the swing here is, so V is VI time, VI over, right? The swing here VE is basically only 1/10 that of VI, right? And if your VI is, let's say, 1 volt or even 100 millivolt, then VI becomes approximately 10 millivolts or 100 millivolts. So, and that can be significant depending on the type of this nonlinearity that you have.
As long as it's pretty high,
As long as the loop gain is pretty high, you are good. But I mean, what is high also is very relative term. So a rule of thumb is if you have to use negative feedback, ensure that L of S is first order. So you don't have to bother with the moment you are trying to push your loop gain to higher and higher frequencies, you run into trouble of getting in, getting closer to other parasitic poles, right? So that's basically the dominant pole approximation that we do, that we ensure that there is one dominant pole and all the parasitic poles are way out of UGB, right? Way beyond UGB. Now, if you keep increasing, pushing the dominant pole closer and closer to higher frequencies, to parasitic poles, you are not going to get that first order approximation. So that's an additional problem. And that, in fact, is the problem why negative feedback at higher frequencies doesn't work as well, right? Because if you have a first order system, you can design it for any frequency, right?
you might start designing a first one of those parasitic poles.
Yes, correct. Yeah. But still, I mean, first order negative feedback loops are still used, right? I will show you one example, which is quite trivial, but I mean, you would readily appreciate why that kind of works. Okay, fine. So let's see what are the other ways of mitigating distortion. So we know that if I have a common source amplifier or simple transistor biased with some voltages, and I plot IDS versus VGS for a fixed VDS. I'm going to get a plot which looks like something, right? So around VT, till VTH, it's VO, and then it kind of increases. And then when VGS reaches VDS plus threshold voltage, you are going to hit linear. And then when it hits linear, it kind of becomes like this, right? Because the equation here is proportional to VGS minus threshold voltage whole square. Here it is V overdrive times VDS minus half VDS square, right? Proportional to that. So, which essentially means that if I have to plot the GM, right? So the GM or the first order derivative of this plot of this curve. So I plot. I am kind of going to get this to be, what will this be to start off from VTH? Before VTH, it is 0. After VTH, it linearly increases, right? So it linearly increases, and then it reaches here, and after that, constant, right? Right? So it's constant. So this is GM with respect to VGS. Now, you should be able to readily understand graphically why this is an issue. Because let's say I bias my transistor somewhere over here, and we apply a sinusoid between the VGS, which essentially means that the sinusoid is something like this. So clearly, this half of the sinusoid, on an average, is larger GM than this half of the sinusoid. Correct? So which essentially means that to a very crude approximation, your output on the right-hand side, the current, the incremental current, this side will be larger than this side. Right? So which essentially is another way of saying that their output will be distorted, right? And this is happening because your GM is not constant across the signal swing. Okay. So now, graphically, you can intuit that what if I had another transistor which had exactly the opposite type of GM, right? What if I had another transistor which had probably a GM like this? Within this range, it had a GM like this. Then summation of these two can be a constant. In fact, it will be a constant if the slopes perfectly match. So can you think of manufacturing a GM or designing a GM which has this kind of okay, differential pair, not exactly. I'll come to differential pair, but far simpler. PMOS, right? Essentially PMOS, right? So if I have a PMOS, which exactly will have this red kind of GM plot. So if I have a PMOS, this is going to have the red kind of GM plot. And if I have an NMOS, this is going to have the black GM plot. And if I sum up the currents, right, which normally is pretty easily done, summing currents in analog circuits is probably one of the easiest things. You just connect the two terminals and ensure that they are not subtracted, just that, right? So you can both subtract or add. But fortunately, in case of PMOS and NMOS, they both add up if you connect it like this. So that's it. So if you do this, then you should be able to get a fairly linear GM, provided their slopes are matching, right? So now, obviously, you'll have to bias it separately, right? So you'll have to ensure that these guys are biased with however your favorite biasing scheme. And then you can apply the input here maybe. Okay. You can bias it through current mirror, you can bias it to resistor divider. Each of them have their own pros and cons. And I assume you know this from your experiences in analog circuits. Now, the question is there any, it looks like this is all good, right? I mean, if I assume, in fact, if you assume these, this mu and C of W by L for the NMOS and the PMOS are identical, then, and further, if you assume a square law model, the second order distortion will completely cancel out, right? Because you are doing one minus the other, right? So the second order distortion is going to completely cancel out, and you're only going to get the first order term, which means looks like it's perfectly linear. But it's not the case. I mean, because you have higher order distortions. So in most cases, the higher order distortions will still persist. But even if I do not assume that, as a designer, what you have to be careful about is to ensure that the strengths of these PMOS and NMOS are identical across process voltage temperature variations, right? Because PMOS is made out of, I mean, it's relying on hole mobility, NMOS is relying on electron mobility. right? They have different threshold voltages and so on and so forth. There's not guaranteed that they will be having identical. Even if you change W by L, it's not guaranteed that you are going to have identical responses, right? So typically, if one uses this, what is generally done is to have a bank of PMOSes and a bank of NMOSes, right? So bank, I mean that you have like multiple of them connected with switches, right? So in the sense that you might have some sort of switches. And you turn on the switches based on your requirement, right? Basically, you are changing the W by L of effective W by L of the top stack and the bottom stack. And obviously, you cannot leave it as is, right? You'll have to ensure that these track across PVT or process voltage temperature variation, which means that some sort of tracking in the background needs to happen. So generally, when these type of circuits are used, they are not generally used in isolation. There is something in the background which is tracking whether these PMOS and the NMOSes are properly sized. And you cannot really sit and tune knobs. Some negative feedback loop in the background does that job. Okay. So a negative feedback loop in the background can do this job because ultimately we are relying on these characteristics, which is a DC characteristics. Right? Since this is a DC characteristics, I mean, if you read some papers, you will see that there is some negative feedback loop, which works in the background to ensure that the DC characteristics track. And it is fairly easy to track DC characteristics using negative feedback because the high frequency requirement is no longer there. Okay, so that is one way of mitigating distortion. Fine. So this is so this is introduce distorted currents of opposite distortion polarity. Right. So this is a generic example of the principle that one is using. Another way of mitigating this is called a feed forward way of. So if feedback doesn't work, maybe do something else. Let's call it feed forward. So what is a feed forward? So by the way, I'm not showing you the exact, I'm not writing equations and showing you the exact things because they don't have much use unless you are doing pen and paper analysis with fairly simplistic models, right? But the key thing is to understand the philosophy behind it, because ultimately when you will be designing, these square models will not be valid. Right? So you'll have to put these things in simulator, but when you turn knobs, you have to understand what you are tuning for, right? So that is a more important thing than writing square law models for these cases, right? Because if I simply use square law models, you'll see that there's no distortion at all, which is not true. Okay, so this is another generic philosophy of reducing a distortion, which is called feed forward way. I'll show you the example, and then hopefully you'll understand why it is called a feed forward way of reducing. So let's say I have a amplifier which has only third order distortion, right? Maybe it's a differential amplifier, right? Which doesn't have any even order distortion. It only has third order distortion. So which means that I can express this output as this is V in, A1 V in plus A3 V in cube. I am neglecting the fifth order and all, right? So fine. So let's say this is plus, the sign is plus. So the goal is to cancel out A3 V in cube. Okay. So if you observe that if I scale V in, right? If I scale V in, let's say by a factor of 2, and then the first order term only scales by a factor of 2, but the cubic term scales by a factor of 8. So there I am getting some difference at the output based on the value of V in, right? So now if I can do some algebra, and the whole idea is to cancel out this A3 V in cube term, right? So basically the idea is, can I find another input which is a scaled version of V in, and do some algebraic manipulation to cancel out A3 V in cube? Do you think it is possible? Yeah, those things. I'm just talking maths now, right? Once you have the maths, we'll probably be able to add paths. So, but mathematically, do you think it is possible? It should be possible, right? Because ultimately, let's say I apply, instead of V in, I apply V in by 2. I am applying V in by 2 because it is easier to apply a scaled down version than a scaled up version, obviously. If I apply V in by 2, your output will be A1 V in by 2 plus A3 V in cube by 8, right? So obviously, I mean, if I subtract this with this, I mean, we are not getting much because A3 V in cube still remains. But if I, let's say, scale the second term, scale this by a factor of 8, and then subtract, then the A3 V in cube term gets cancelled and only the A1 V in term remains. Some scaled version of A1 V in terms remains, right? So that's the philosophy. So how can I do that? So I can have another path, which is probably a scaled down version, which is divided by 2. And this need not be divided by 2, it can be divided by whatever you want, but the scale up version will change. And then maybe have a negative 8, and then add them up. So this is a block diagrammatic representation. If you have to do I mean, slightly more realistic representation, then we know that most of these amplifiers are essentially GMs, right? So I'll just replace them with the symbol of a GM. Divide by 2, you can do either a resistive divider or a capacitive divider, right? Resistive divider can have an issue because you can have noise effects, right? So you can have cap divider or resistive divider, provided these capacitances are not large enough to load your input. That is another constraint if you are designing. And then so this is V in over 2. So then the next goal is to, once we get V in over 2, we have to essentially have another block which has the same type of nonlinearity as the first block. Otherwise, if the second block also has a different nonlinearity, then I have a problem. So the best way to ensure that the another block that you are going to use has the same type of nonlinearity is if that one has is basically a replica of the first block, right? So I can have the same, so I should write here G3 V in cube also. If I have a replica of the first block, that is not sufficient because I have to scale the output by a factor of 8, right? So then you might say that I will use an amplifier of 8. That is not possible because if I had that, I wouldn't have done all this. So, but the easy way to do is saying that I will probably have a set of 8 of them in parallel. And these are all spitting out currents. Current addition is simple. You connect the outputs of an OTA. And you count this. The effective current that comes out. This should be in opposite polarity, right? So this has to be negative, negative, negative because you're subtracting. The effective polarity that will come out is this path. I mean, G3 V in cube term will get cancelled, but the part that will remain is only the scaled version of GMVI or GMV in. So you are going to get factor of 4 from this path and minus factor of 1 from the top path. So you are going to get 3 GMV in. and V in cube term will get cancelled. But do you see an issue with this? This works, by the way, and this is actually used in regular practice. But there are potential issues with this. Whenever you come up with a solution, you should also be aware that what are the limits beyond which you cannot use. Yeah, your power definitely is high, right? You are using essentially 9x the power consumption than what you had earlier. Surely you are getting like you are getting, if I check in terms of SNR, right? So you are getting signal is also 9x, right? Signal power is also 9x because 3 is GM whole square. Right? In terms of power and signal, that proportion is still the same. But the issue is that now you have extra noise contributors. Right? Earlier you had only one noise contributor. Now you have like 9 noise contributors. So you are going to get a hit at SNR level with respect to power. Right? So that is one problem. The second problem is I have limited this discussion to only third order nonlinearity. Right? That did not necessarily be the case. In fact, that's never the case because you cannot really choose a device and say that I want only third order from you. It is going to give you fifth, sixth, everything. The moment it gives you fifth, sixth, everything, if you do, let's say you assume you have a fifth order nonlinearity. So clearly this is not going to cancel out the fifth order. In fact, it's going to amplify the fifth order. So if you have if your signal swing is not limited so as to ensure that the fifth order nonlinearity is small enough, then this is going to kill you. The fifth order is going to kill you. Okay. So this is, so these type of solutions work under certain input conditions, but not always. But useful solution. If you know that the input is limited, it doesn't go beyond some range, this is used. The other thing that I have not, for all these, not only for this, for all the, even the previous case and this case, basically the inverter case and this case that I didn't consider, is that I only assume the distortion because of the V overdrive change, input distortion, basically, right? When I say input distortion, I mean the VGS is changing, the GM is changing, the distortion arising because of that. But you also have the thing of GDS distortion. Because if your output swings, your VDS changes. If your VDS changes, then obviously the current, which is, if you assume channel length modulation, right, which actually is the case in very short channel devices, which means your VDS changes. There is you have distortion due to that, right? So these type of cancellation is not going to take care of VDS related issues. Okay. But if you can do negative feedback takes that into account also because it doesn't know from where the distortion comes. It basically, whatever it sees, it tries to mitigate. Okay. Okay, fine. The another interesting thing that people have explored is it boils down to the first equation that I wrote today, that IDS is proportional to VGS minus, or rather, let me just write threshold V overdrive. V overdrive whole to the power M, where M is between 1 and 2. Right? Again, a model. Right? So if you go and check out the exact models, they are not expressed in this way. They have some numerator, some denominator and all. But if you curve fit, you are kind of within some range, you are going to get a fitting like this in saturation. So if this is the case, the GM is then proportional to M VOV whole to the power M minus 1, right? So, and your G2 is proportional to M into M minus 1 times VOV to the power M minus 2, and G3 is proportional to M into M minus 1 to M minus 2 times VOV whole to the power M minus 3. Okay, so now can you comment on the sign of G3? Assuming M is between 1 and 2 is negative, right? Fine. So G3 is negative, right? So this is less than 0. Correct? So this is assuming transistor is biased in saturation. Now, I assume you also know this if the transistor is biased in subthreshold, right? So in subthreshold, what is IDS proportional to? Yeah, right. So you have V overdrive, or rather, not V overdrive exactly, VGS, whole to the power some factor, right? Sorry, E power VGS over VT. Yeah, it's VT only, right? So where VT is KT over Q, right? In this case, VT is KT over Q, not the threshold voltage. Right, that is a constant, right? So I'm leaving all the constants out, let it be. So the reason I'm leaving it out is because if I have to find out G3 is proportional to, in this case, whatever something times VGS by VT times e to the power VGS by VT. And the sign of this is positive or negative? This is positive. The reason this observation is important is because if I plot G3, if I plot G3 with respect to V overdrive and let's VGS, not V overdrive, with respect to VGS, let's say this is threshold voltage. So clearly above threshold voltage, right? Somewhere in saturation, when transistors are in saturation and you are above threshold voltage, your G3 is negative. Below threshold voltage, simplistic model, right? Obviously, these models don't really start here and stop here. It's a gradual stuff. Below threshold voltage, your G3 seems to be positive. So clearly, when you are going from subthreshold to inversion and you have moved into saturation, somewhere it has gone from positive to negative. I don't know where, but it has gone positive to negative somewhere, which means there is a zero crossing somewhere. That's the important thing, observation. So if you can bias your transistor at that zero crossing of your G3, which is the sweet point of V overdrive for which G3 is equal to 0, you are not going to get any third order distortion. Right? So this, in fact, I mean, the issue obviously in this case is that you cannot predict where this guy will be, right? You change process voltage temperature, this guy is going to change, this point is going to move around. But having said that, if you have a preliminary idea of where it can be, you can probably bias it. You might not hit G3 equal to 0, but can hit a decent enough, low enough G3, right? Another argument in this favor is that if you have the option of trimming the circuit, by trimming, I mean, once the tape out happens, when the chip comes back, let's say you have some variable bias and you have the control of changing the bias, then maybe you can change the bias and move the circuit back to this sweet point, wherever you want it to be. But again, you do not want to keep doing that because temperature can change and temperature will change, and this point can also move. So if this has to work, then there has to be a background loop which tracks this again. So none of these circuits which are used in products have this open loop way of biasing. They will have a feedback loop running somewhere in the background to extract the value of G3 and biasing it, right? So I'm not expecting you to design that circuit, but it's good to know what are the knobs to have. Okay, so this is again often referred to as G3 equal to 0 biasing, right? Okay, any other questions?
Some sort of like calibration.
It is calibration. It is in fact calibration. But again, the issue here in this case, this cannot work for high power circuits, because for high power circuits, you need very high value of VGS, obviously, because you want to extract maximum power out of your MOSFET. This clearly works somewhere around subthreshold, right? You are coming out of subthreshold, moving into inversion. So fairly low amount of V overdrive. Right? So that is one limitation. The other limitation is that, again, we haven't talked about what is happening to G5. So this is counterintuitive, because the first point that I told you is increased V overdrive, right? But here it looks like at a fairly, near subthreshold, which is very low value of D over drive, you are getting a very sweet G3